Hello everyone, I'm Dr. Sayantika Chowdhury. Have you ever written a line of code and just wondered, how does the computer actually get it? How does it turn your thoughts into actions? Well, today we're going on a special tour. We're going inside the computer's kitchen to learn the secret language of its head chef, the CPU.
Look at this. Think of all of computing as different layers. Way up at the top, that's where we live, writing in languages like C, Java, or Python, stuff that makes sense to us humans. But deep down at the bottom is the hardware, the actual circuits and wires. Our job today is to peel back those layers in between and see how our instructions make that journey from our screen right down to the silicon.
So here's our plan for this tour. First, we're going to learn the secret language of the machine. Then we'll look at the basic commands, the actual verbs of that language. After that, we'll see how the computer organizes all its data. Think of it as kitchen management. Then a really cool trick, creating reusable recipes. And finally, we'll talk about why knowing all this is going to be a game changer for you. Ready? Let's begin. All right, first things first, we need to solve the biggest communication gap in the world. How do we, with our complex ideas, talk to a simple processor? How do we tell the head chef what meal we want to create? Well, at the very, very bottom, the CPU understands only one thing, machine language. And it is incredibly simple. It's just a long sequence of ones and zeros. That's it. Think of our head chef having a kitchen where every single switch is either on or off, 1 or 0. It's the most basic language possible, but it is the absolute truth for the computer. Everything else is built on top of this. Now, trying to write a program in just ones and zeros would drive anyone crazy, right? So we clever humans created a bridge called assembly language. It's basically a human-friendly shorthand. Instead of remembering a binary code like 10110, we can just write a simple word, a mnemonic, like add. So now, instead of flipping switches, we can give simple orders like heat the pan or mix the ingredients. And this is where it gets really interesting. Look at the difference. In a high-level language, we write something so simple. C equals A plus B, one line. But for our CPU chef, that one thought is actually a 3-step recipe. First, you have to move ingredient A into a temporary mixing bowl, which we call a register, R0. Then you add ingredient B into that same bowl. And finally, you move the result from the mixing bowl, R0, into the final serving dish, C. See that? One of our ideas becomes multiple, tiny, precise steps for the machine. Exactly. You've got it. Assembly language is that perfect translator, that bridge that connects our world of complex ideas to the processor's world of simple, one-step-at-a-time actions. Okay, now that we understand the language, let's look at the words themselves. What do these individual commands, these recipe steps, actually consist of? Well, pretty much every instruction has 2 parts, just like a simple sentence. There's the verb, the action, which we call the operation. Think of it as chop. And then there's the noun, the thing you're acting on, which we call the operand. So that would be, say, onions. So the full instruction is chop onions, operation and operand. That's it. And these commands usually fall into a few main groups. You have your data transfer instructions, which is just moving ingredients around. Then you have arithmetic. That's the fun stuff, mixing and combining. Logical instructions are for making decisions, like checking if the oil is hot enough. Program control is really powerful. It lets you skip ahead or go back in your recipe. And finally, you have things like shift and rotate, which are for really precise, fine-tuned actions, kind of like finely dicing a vegetable. All right, so we have our recipe steps. But a chaotic kitchen is a slow kitchen. A great chef needs to be organized. The same is true for a CPU. It needs a system to manage all the data it's working with. One of the most important organizational tools is the stack. Now, a stack is a special kind of list where you can only access the very top. This is a strict rule called last in, first out, or LIFO. What does that mean? It means the very last thing you put onto the stack has to be the very first thing you take off. The absolute best way to picture this is a stack of plates at a wedding buffet. When the staff adds a plate, they place it on top. That action is called a push. And when you come to take a plate, you take the one from the top, right? That's called a pop. You can't just pull a plate from the middle of the stack. The whole thing would crash. You can only ever touch the top one. That's a stack.
But what if the order matters? What if it's not about the last one in, but the first one? For that, we have something different, a queue. A queue is just like a real-life queue. You join at the back, and you get served at the front. It follows the principle of first in, first out, or FIFO. So let's put them side by side. A stack is like that pile of plates. The last one on is the first one off, LIFO. But a queue is like the line of order tickets that come into the kitchen. The chef has to handle the first order that came in first, right? That's FIFO. One is a pile, the other is a line. Two different ways of organizing for two different purposes.
Yes, that is a brilliant way to put it. You've nailed the use case. A stack is perfect for when you get interrupted and need to remember where you were. A queue is perfect for fairly processing a list of jobs, one by one. You know, the best chefs and the best programmers share a secret. They are lazy in a smart way. They hate doing the same work over and over again. Let's see how they do it.
No way. Of course not. Can you imagine how repetitive that would be? Instead, they perfect that one recipe for basic curry paste, write it down once, and then in every other recipe, they just say, add 2 spoons of basic curry paste. Programmers do the exact same thing.
And that master recipe, in our world, is called a subroutine. It's a block of code that does one specific, common task. So instead of writing those lines of code again and again in your main program, you just call the subroutine whenever you need it. It's a huge time saver and keeps your code clean and organized. And the magic happens with 2 simple commands. Call tells the program, okay, pause what you're doing and jump over to this subroutine. Then, once the subroutine is done, the return command says, all right, job's done, now jump back to exactly where you left off. But wait a minute. How does it know where it left off? How does it remember? Aha! And this is where it all comes together. It uses the stack. Remember our stack of plates? When the chef decides to go make that curry paste, they take a little bookmark, place it on the main recipe page, and push that bookmark onto their stack. Then, when the paste is ready, they simply pop the bookmark from the top of the stack, and it tells them exactly which line to return to in the main recipe. Isn't that elegant? It's such a simple, beautiful solution. Okay, so we've toured the kitchen, learned the language, seen the recipes and the organization. Let's step back for a moment and talk about the big picture. Why is any of this important for you as a future electronics and communications engineer?
Because knowing what happens under the hood is like a superpower. You'll write better, faster code because you'll understand the real cost of every instruction you write. You'll be the one who can debug those mysterious, horrible bugs that nobody else can fix because you'll know to check the stack for an overflow. This is what separates a good programmer from a great engineer. This knowledge is essential if you want to work on embedded systems, IoT devices, or anything where performance is critical. You're building the foundation for your entire career right now with these concepts.
So I want to leave you with this thought. Every single piece of technology you love, your phone, the apps you use, even the giant AI models that are changing our world, every last one of them is built on the simple, powerful ideas we talked about today. These aren't just old concepts, they are the timeless foundation. As you move forward in your careers, never lose that curiosity to understand how things really work at this deep level. Because you aren't just learning to code, you are learning the fundamental language of creation in our digital universe.